In this video, we're going to look at differentiability and what makes a function differentiable. So differentiable basically just means that the function has a derivative. Now we're going to consider things like differentiable at a point. And that's what we're going to sort of focus on in this video. And so the derivative is defined at that point. And we could also consider something like differentiable on an interval. Or even going further to say like a differentiable function. And this just means that it'll be differentiable. It has a defined derivative at all points in the interval. Or for differentiable functions, all points in the domain. And some things that are useful to consider here. So if it's differentiable, we basically need a tangent line. It needs to be able to have a tangent line. The slope of the tangent line needs to be defined. And something else that we'll get into more, it needs to be what I'm going to call smooth for this point. I'll get more into this at the very end of this video. So instead of going more into differentiable, let's look and see what would make a function non-differentiable at some point. Any discontinuity, any breaks, would make a function not differentiable at that point, because let's consider a removable discontinuity. You can't have a tangent at this point because this point doesn't exist in the function, so it can't intersect the function there. Okay, now an example of a function that has discontinuity would be something like so let's see, example, f of x equals the absolute value of x divided by x at x equals 0. And let's look and see what that looks like. So in there, we have this graph. And you can clearly see there is this jump discontinuity at 0. And if I were trying to make a tangent line here, I say, okay, am I going to try to brush it up over here, brush it up over there? Does it connect these? And no matter what I think of, I can't have this line that's going at the same instantaneous slope because we're not even defined here in this big old jump. So this is not differentiable at 0. But everywhere else it has a derivative, and its derivative is 0 because it's horizontal. All right. Corner. So any corner is not differentiable, and corners look like this. The reason is at this corner, let me get rid of that and put this sort of red. I don't know what's the best tangent line. I don't have it able to sort of brush up against the curve. If I try for this tangent line, which is maybe the best option, we don't really have any reason that this tangent line is any better than something like this, or even something like this that actually matches the slope on at least one side. And so since there's not a single tangent line, I don't have it able to sort of brush up best against the curve, this is not differentiable at that corner. And an example of a function that gives me a corner is simply the absolute value of x at x equals 0. And let's look at that. So let me get rid of this one. And here. And you can see at 0 we have this corner. It's a corner because I have a finite defined slope on one side, and on the other side they just don't match up. Okay, a cusp. Well, a cusp is like an extreme corner. So in here, a cusp, it sort of comes in and goes almost vertical and turns around. So it looks like a corner, but instead of coming in with a nice defined slope from both sides, it actually goes towards the vertical undefined slope here. And this one doesn't show up a ton, but there are some simple functions that get you that. For instance, f of x is equal to x to the 2/3 power at x equals 0. And it basically gets this because it takes the cubed root and sort of squares it, which makes everything positive. So let's look and see what happens with this. That would be this function right here. And you can see as I look in near 0, it does seem to sort of get very close to vertical. Not just a corner, but sort of a complete turnaround. The final way we'll get something that's not differentiable is with a vertical tangent. And the simple idea with that is you have to recall that vertical lines have undefined slopes. So if the derivative is the slope of the tangent line and the tangent is vertical, then it won't be defined, so it will be non-differentiable. You can't get a slope, a value for a slope if it's undefined. And something like this would have a vertical tangent right here. Now, a simple example of this would be something like f of x is equal to the third root of x. Again, at x equals 0, I just made these simple parent functions, but I could do some transformations to move that around. And if I look at that function, it looks like this. And you can see right in here at 0, it gets to be actually vertical. I want to stress something here, though. This function looks a lot like arctangent. And arctangent does not have a vertical tangent. So inverse tangent of x, so this function is differentiable everywhere. It looks similar to this, but the thing is, the steepest slope that arctangent gets, let me put that in here and I'll change this function to arctangent briefly. So arctangent x. The steepest slope it actually gets here is a slope of 1. So arctangent doesn't have this not differential point. There is a very clear difference here. And in a lot of pre-calculus courses, they don't stress the difference here. It's sort of good enough, but now we do care about this. Okay. So, something to talk about here. Differentiable implies continuous. It's worth knowing this. So, if we know f of x is differentiable at x equals x naught, or over an interval or anything, then we know f of x is continuous there as well. And the simple reason for that is, if f of x were not continuous there, it couldn't be differentiable because you couldn't have the tangent line. But it's worth noting this does not work the other way. So this is not necessarily true. I'll say in reverse, the converse of this statement, where I say continuity does not necessarily imply differentiability. And a simple counterexample is just like the corner. This is definitely continuous, but not differentiable at this corner. All right. Last example, or last idea here is the term locally linear. And locally linear means that, let me say it this way. If a function is differentiable at some x value, x equals x naught, it behaves like a line if you zoom way in. And this behaving like a line actually makes the function look smooth. So let's see this. Let's go back to our, well, this one is too easy. So for this, of course, if I start zooming in along here, it's linear to the right and to the left as I zoom in. Well, look, it still looks linear. So that's no big surprise. Nothing big here. But if I try to zoom in around these points where it's not differentiable, you can see as I zoom in, it doesn't start looking more and more like a line. It still looks sort of like a ray, missing the end point. So that's the idea with this, is this one definitely looks linear there. And same for this. As I look at any of these points up here, of course, as I zoom in, it just looks like a bam line. Okay? But if I zoom in at the corner, it never begins to look like a line, so at the corner, it's not differentiable. And the same thing holds, so this is finally going to be an interesting example for this. As long as I'm not zooming in at 0, the curves will eventually begin to look like straight lines. So I'm going to zoom in at this point, let's say 1, 1. As I zoom in, eventually the curve begins to look more and more straight until on this, it's almost indistinguishable from a line. And no matter where I look, if it has a derivative, it has to behave like a line close. So if I go further out this way and I zoom in, you see, oh, okay, now it looks almost exactly like a line. Zoom back out. But if I zoom in at the cusp, no matter what I do, it's never going to behave like a line. It just gets to be a more and more extreme V shape. This is what a cusp does. Okay, so I'll zoom back out. Now it's worth noting here, no matter where I zoom in here, I do get it looking like a line. So I'll pick right here where it seems to have a pretty harsh curve, and as I zoom in further and further, the curve seems to straighten out until we get a line. But you'll notice I phrased it very carefully. I said, if it is differentiable, then it's locally linear. It's also locally linear at 0. You see as I zoom in, it starts to begin to look more and more like a line. However, just because it behaves like a line, if it behaves like a vertical line, it still is not differentiable there, because vertical lines have undefined slope. The derivative is the slope, so the derivative would be undefined. So as long as it's smooth, you can get tangent lines on it. If you have any sharp points or turns, that's where, no matter how much I zoom in, it'll never straighten out. Alright, I hope that this helped you guys out. Feel free to comment below if you have any questions.